Okay then, so hello and welcome. I hope you're all doing safe and well at home. So it's great to see you here. Thanks for joining today's SQL Office Hours session. As always, this is a chance for you to ask me your questions about SQL, and we have a topic in general that we cover. So this time we'll be talking about statistics or optimizer statistics and why, even when you've got nicely up-to-date stats, the optimizer can still get its row estimates completely and utterly wrong. So we'll be looking at how to do that. Got questions, put them in the chat or the Q&A window. If you put them in the Q&A window, then everyone can see them generally, so that's slightly preferable. But just feel free to reach out and discuss ask questions about what we're covering today. So let me go back to the slides quickly. So let's get that up and let's get going. So what I'm going to do to start off with is just jump into a demo to show the kind of problems that this might have. So let me just make sure I've got my table all created up and ready. So I've got a table, classic bricks table, just to prove like nothing up my sleeve. There really are up-to-date stats on this table. Let me just gather stats on that. And I'm going to run a series of queries. And for all of them, the optimizer is going to get its row estimates very, very badly wrong. Okay, so we'll start off with a simple count of all the rows which have the color red. So we do that, and we can do that with the auto trace. We'll get the execution plan, which shows us how many rows the optimizer thinks it was going to get and how many rows it actually got. So we can get the cardinality and the last output rows, compare those. And those are broadly, ideally you want these to be broadly similar, rough, same order of magnitude. And we can see here we've got an estimated cardinality of 3,500 rows, but the query actually returns 9,000 rows. So we're getting about a third the number, or 3 times more rows than the optimizer predicted that we would get. So not done too well there. Let's just pin that to save that for later use. Let's see what happens when we add another column to my query here. So look for red cylinders. Run the plan for that again, and the cardinality is now dropped even further, down to just over 1,000. But we're still getting 9,000 rows, so we're now out by nearly a factor of 9. Okay, so estimate's gotten worse. Number of rows we're actually returning stays exactly the same. Okay, so this isn't very good, is it? Let's look at a couple of other ones. So let's look at a couple of range-based queries. So we want to find all the rows with these brick IDs between 0 and 1,000. So we do that, and we're estimating 500 rows, but we've actually got double that, so 1,000 rows. And if we look for another batch here, so 9,000 up to 10,000, again, we're going to estimate basically the same number of rows, so 514. But we get just one row this time. So we've gone from one extreme to the other. Double the number of rows down to just basically 0 rows, 1 row. So it's not done very well here at all, has it? So let's jump back to the slides and look at some of the reasons why this might happen. Alrighty then. So we can see, had quite a few examples where the optimizer just got its row estimates completely and utterly wrong, despite having up-to-date stats. First thing I did was gather stats before running any of those queries. So it's not because I've just tweaked the stats in some weird way or they're out of date or something like that. Nope, they are fresh stats, but the row estimates are still wrong. So what's going on? Well, by default, the optimizer has a number of calculations that it performs. And if you're checking that a column equals a particular value or a number of columns equal particular values, it has a formula a bit like this. It says how many rows are there in the table altogether, how many number of distinct values, number of different values in column 1 times the number of different columns in values in column 2, column 3, and so on. So multiply all those together and divide the number of rows in the table by that. So that gives us the fraction of the rows we expect the query to return. And there's other subtle variations on this. There's slightly different formula if you're searching for the between, so a range of values. I haven't accounted for nulls in this either. But principally, the problem here is the optimizer thinks there's an even spread in the values. So it expects similar doesn't matter which value we pass for a column, expect basically the same number of rows, whether we pass searching for red bricks, green bricks, blue bricks, whatever, and expect, basically speaking, the same number of values. There are several problems which can mean that just isn't the case. So the three that we're going to look at today are value skew, range skew, and correlation. And we'll start off with value skew. So this is the one that we're probably most familiar with. So I've got a table full of bricks here. I've got lots of different bricks. So you can see we've got some red, some green, some blue. See that there's only a handful of blue ones, so about 4 of those, quite a few more green, and it looks like there's probably more red as well. So if we're searching for all the red rows, we're going to get a lot more rows back than if we search for the blue rows. So that formula where we just say, well, how many different values are there, and divide that, the total number of the rows, by that, we're just going to get a completely inaccurate estimate. We need to account for the fact that some of the values are more common, more popular than the others. So how can we do this? Well, we can start by gathering a histogram. So recording for each color we've got how many rows there are. So we sort them into 3 different buckets, as we call them in Oracle database, and say for each color how many rows do we get. So we can count them all up, and you see that we've got 4 blue rows, 8 green, and 14 red. So actually we've got more red rows than blue and green put together. So this is a much more common value. Now we've got this, the optimizer can use this information to get much more accurate estimates. So this is a frequency histogram. We record what the values are and exactly how many rows have that value, at least at the time that we gather the stats. So these work really, really well. These give really, really accurate row estimates. For example, if we search for one of the colors we got, so blue, the optimizer can just look for that histogram and go, okay, we've got our entry for blue. There's 4 rows in that bucket. So there's going to be about 4 rows in the table for that value. So it will give a reasonably accurate estimate. Same for green and red. So what happens if we search for a value that's not in our histogram here? So for example, we search for pink. Well, it can kind of go and look, well, I know there is no value pink here, so I'll estimate that we get very, very few rows for this. Now notice I haven't picked 0 here. I've picked 1. Well, why is this? Well, if we estimate 0, then as we work our way up the plan, the optimizer can multiply or divide these cardinalities by other cardinalities for other tables. So how many rows we expect from this table by the number of rows we expect for other tables, and so on. If we return 0 for this, then this can lead to all sorts of other problems in the plan. We're going to get zeros elsewhere in the plan, or potentially divide by zeros problems as well. So it's always going to estimate at least 1, because 0 introduces a whole bunch of problems. But we know value that we didn't see when we gather stats last time is probably very, very rare. So we're going to get very few values, or expect very few values. So these frequency histograms give very, very accurate row estimates, and they work really, really well. But there's a problem. There is a limit to how many of these different buckets we can create, how many different columns we can store exact row counts for. So by default, that's 254. Just to help follow what's actually going on here, let's just assume we're limited to a maximum of 3. It gets a bit difficult to visualize if I'm trying to show 254 colors on the screen, so we'll stick with just 3. So if we're limited to just 3 buckets, what happens if we now insert another value, a different color, so yellow? Well, 4 into 3 doesn't go, does it? So what can we do here? Well, there is a little trick we can take. If we've just got 1 yellow row, then actually that's basically the same row estimate as for values which don't exist at all, colors that don't exist at all, such as pink. So if we've got just 1 row, or very, very few rows for a particular color, we can ignore it. We can just exclude it from our histogram completely and still get a reasonable estimate for it, just because is very rare, very uncommon. And in this case, one yellow, we're going to estimate one for any other color that's not in our histogram. So we just ignore it. So this is a type of histogram we introduced in 12C called a top frequency histogram. So what the optimizer does here is really rare values, it excludes from the histogram completely. So this gives frequency-like behavior for our common values, but those that are unusual don't appear at all. And it generally doesn't really matter. So this, if we've got most of the values cover, or most of the rows have a small number of values, and there's a few which have unusual values, we can use this top frequency behavior. So a question from Ashish, you mean each column can have 256 values in a table? No, that's not what I mean, Ashish, sorry. You can have as many different values in each column as you want. You can have millions, billions, trillions of different values in a column. But when it comes to creating our histogram, recording how many rows have each individual value, we cannot, there is a limit to how many of those we can store. So how much we can gather statistics about. So that means when we've got, let's say there's a default limit of 254, that means we're only going to have 254 of these columns in the histogram. The table itself can still have a vastly more values than that, but we're only going to record the exact count for 254 of those. Okay, so Brian Brock, please forgive my ignorance, but why should I care if the optimizer gets the estimates wrong as long as I get accurate data in the end? What is the value of the estimate in the first place? That's a good question, Brian. So the row estimate drives a couple of things, or a few things. How it's going to access the data. Is it going to use an index versus a full table scan? How it's going to join the tables, which order it's going to join them, and which type it's going to use. And how many rows it thinks it's going to get from table is a key driver in those decisions. Now, the thing is, if it's got the right plan, then actually, you're right, it kind of doesn't matter. But a lot of the times when it's got the wrong plan, a very common reason for this is because it's got its row estimates wrong. It's estimated lots of rows when in fact you've got few, or vice versa. You've got estimating few rows when it's got lots, which has led it to choose an index when it shouldn't have done, or choose the wrong join type, the wrong join order. So if the plan is fine and performance is good, then actually you don't care. It doesn't really matter. But this is generally when the plan is wrong or bad, incorrect row estimates are a very common reason for that. So this is why you kind of care, because in the cases where it is wrong, that is probably a leading cause of that. So I hope that answers your question, Brian. But yeah, you're right. If performance is good, it kind of doesn't matter, right? Okay. You only need to look into this when you've actually got problems. Okay, Ashish, you mean you can each column can have 256 distinct values in a table? No. I mean, come back to this. I'm going to talk a bit further, Ashish. Maybe it will help make things clearer. Like I say, there is absolutely no limit on how many different values you can store in a column. You can have millions and millions and millions of them. Okay? There is no limit to the values stored in the table. What matters for the statistics. So as we move on, hopefully it'll become a bit clearer about what I mean here. All right then. Anonymous, is there a way to get estimated and actual rows? Come back to that one, Anonymous, estimated versus actual. I'll go back to the demo and I'll show you what that means. Alrighty then. So that was our top frequency when we've got just one yellow brick. But what if we insert a whole bunch more? So I've got 3 more. So we now got 4 yellow bricks. So that's the same number of yellow bricks as we've got blue. I can no longer just ignore that and get a reasonable estimate, right? Because yellow and blue are the same number of rows. So yeah, I can't just go, we'll just ignore yellow and still expect to get a reasonable estimate there. So what can we do? Well, instead of having one of these columns, one bucket for each value, each bucket now needs to store a range of values. So What we'll try and do is spread the number of rows evenly between the buckets. So we'll stick with 3 buckets here, and distribute them, we'll sort alphabetically and split the rows across them. So we end up with something like this. So we had 30 rows, three buckets, 10 rows in each. And notice, so the first one covers the values blue through to green, then we got green through to red, and red through to yellow. And the key thing here is, as close as possible at least, we have the same number of rows in each bucket. But each one can span multiple different values. All we really know is what the last value is. And this is a height balanced histogram. So same number of rows in each, but each covers a range of different values. And this was the what we had for a very long time. For a long time, you only had frequency or height balanced histograms. As I said, frequency histograms are great because you know exactly how many rows there are for each value. Height balanced histograms, not quite so good. It's more of a probability function about how many rows we're actually going to get. Because all the optimizer can see is how many rows there are and the value for the last row in each bucket. So all it really knows is we've got 10 rows here, the last value of which is green. We've got 10 here, the last value is red, and the 10 last value is yellow. So all it really knows is we've got 1 green row, 1 red row, and 1 yellow row. It sort of knows we've got 1 blue row because we can see the minimum value for the column as well. But it doesn't actually know how many rows within this bucket have each value. So if we search for how many rows red, well, there's quite a wide range of possibilities here. It could be that it's just this one row at the top here which is red. It could, so we could have just one. The other extreme, all the rows from in this column could be red, and all of them in the second column could be red up to this one here, which is yellow. So it could be anything between 1 and 20 rows which aren't actually red. It kind of makes it a bit tricky to really know or get accurate estimates for how many rows have this color red. Similar problem for green. Yellow, well, we know that there's at least 1, but there's a maximum of 10 because there's 1 over here and 1 on the last column. So this is a problem for getting accurate row estimates. So what can we do about this? Well, we can see green and red bricks spread over 2 buckets. So what better to do is redistribute the rows so that values only appear in at most 1 bucket. So if we move our green from the bottom of here up to one on the left, similarly for the red, move them all into the same bucket. So we end up with something like this. So now we end up with a different number of rows in each bucket. So previously, as close as possible, we'd have the same number of rows in each of these columns. Now we've got wildly different numbers of rows in each one. Like, well, how does that help us? Well, as part of the process for doing this, we know we're going to capture the total number of rows, but also how many rows have the last value in that bucket. So we can see there's 12 rows in this first column here, but 8 of them have the value green. So we know that there are 8 green bricks, 8 green rows in this table. We know here there's 14 rows and there's 14 red, so actually we've got frequency behavior with this. So we know we've got only red rows in this bucket. Similarly, we know we've only got 4 yellow here. So this gives us much better accurate estimates for these common values. So red and green, we can see exactly how many rows have those values. So this gives us frequency-like behavior, even though we're working over a large range of values. So it doesn't help entirely. Like I say, we don't really know how many blue bricks we've got here. We know the minimum value is blue, so we know we've got at least 1, but is it 1, 2, 3, 4? We don't really know. Also, we don't know what are some other values like brown, which are snuck in here. We just don't know. But it's a much smaller problem. For these common values, we see exactly how many there are. So this is a hybrid histogram. And again, this is something we introduced in 12C, and these basically completely replaced height balanced histograms because they are much better they give much more accurate row estimates. So if you're on 12C or higher, you will only really see height balanced histograms if you've upgraded from an old release and preserved the histograms you had before, or if you've done some specific things to ask for them. You will almost never see height balanced histograms from now on. You'll almost always see these hybrid histograms. So if we look at a table, you'll quite often find that you'll have a range, various different column index histograms on the table. So I've just noticed I've mislabeled my things here. So this should be column here, which columns we've got and what their histograms. Forget these titles at the top. Didn't fix that. I nicked another slide and didn't change it. Sorry about that, folks. So any questions or comments on that while we before I move on? Okay, so let me So Ashish, how does the optimum decide which value of 254 stored is based most used data? I'm not quite sure what you're asking there, Ashish. If you could clarify what you're looking for. 254, if you're asking where does that number come from, it was just a number that was picked as a reasonable value back in the day. I don't know if there's any specific reason for that. If it means something else, please clarify. Okay, let's see. Okay, so estimated actual rows, we'll come back to that in a second. And how to identify the driving table, how to decide which table should be the driving table. So the driving table will be the top one. If you've got a join, I assume you're talking about join here, you'll have two tables. The driving table is the top table for that. So if you look at your plan, you've got nested loop, hash join, whatever it is, table 1, table 2. Top one will be the driving table, and the optimizer chooses the table that returns the fewest rows. So which table are we going to get the least rows from, or at least it prefers to. That's what it aims to do. So hopefully that answers your question. We can, if we've got time at the end, we can come back to that a bit later and discuss that further. Alrighty then. So we'd have these different histograms, and you can see color and shape, we've got frequency, but we've got brick ID, and you see we've actually got a hybrid histogram on that. And you're kind of like, hang on a second, brick ID, that's like the primary key of the table, right? So why would we have a histogram on that? I was talking about duplicated values. By definition, there can be at most one row for each value. So why do we have a histogram at all? Why is that even possible? Well, we've talked so far about value skew. Some values will have some rows which have, some values will have far more rows with that. So we have a lot more rows which are red in the table than those which are green or blue. But what about our unique values? Why do we have that? Well, have another type of skew, and that is range skew. So this is when there's an uneven spread across a range of values. So let's take an example of this. So we've got our bricks numbered 1 to 20. So these are our brick IDs. We'll start at 1, go up to 20. Let's imagine we just go and delete a whole bunch of them. We now have a big gap in the numbers. If I search for all the rows with those values from 1 to 10, the query is going to return no rows. But without any kind of histogram using the default stats, it knows what the smallest value is, 1, and the largest, 20. It's going to assume we're going to get roughly a quarter of the number of rows then in the table, when in fact we're going to get none. Okay, we have significantly overestimated how many rows we're going to get. And this is a problem wherever we search in the table. You know, if I search for 16 through to 20, again, it's going to think that actually that we're going to get about a quarter of the rows, when in fact we are going to get exactly the number of possible values, so 5 or whatever the range of values we've got is. Because it's going to go, okay, we've got 20 values, we've got 14 odd rows, you know, eventually figure out what your range is and divide through, take the ratio appropriately. So without a histogram to do that, we've got no idea about this kind of gaps or holes in the data. And this is something that's actually fairly common. You know, even if you basically never delete rows, which is, you know, there's quite often a lot of tables where you almost never delete. It's still quite common to end up with gaps from sequence assigned primary keys, just to do with the way that sequences work. You've got your values cached. Every now and again, you're likely to lose some. The cache will expire, and you'll jump a big number of values. Whether that happens and how often that happens depends on how busy your system is and what your cache value is, and so on and so forth. But it's quite likely you will end up with gaps in your primary key values like this, even if you never ever delete some rows. So this, if you've got these queries searching for ranges like this, you can end up with problems like this. Now, I say problem, this isn't necessarily always a problem. You quite often have queries which say something like, find me all the rows inserted with an ID greater than whatever, the last time we ran this query, for example. So find me all the rows with an ID greater than or equal to 16. So we do that, we say greater than or equal to 16, there's actually 5 here, but the optimizer is going to scale that down and underestimate this. Now, quite often when you run that type of query, find me the most recent rows, you're expecting a small fraction back. So in fact, an underestimate can be a good thing here, because it's more likely that the optimizer will use an index. Fewer rows we're expecting, the more likely it is to use an index. So actually, in some cases, it can be a good thing that we're underestimating. It's not always bad, but in general, we've got incorrect row estimates, and for some queries, this will cause you a lot of problems. So we can end up with a histogram on this too. So what we've done is split across ranges of values. Now, the thing to note here is look very carefully at the values across the bottom. The first bucket spans the values 1 to 11. The next is 12 to 16, then 17 through to 20. So we know if we're searching for a value between 1 and 11, well, that's split across just 5 rows. So we're going to expect far fewer rows if we're searching in this range than if we're searching in the 12 to 16 range, and so on. And so this can mean that you get these histograms on unique values, even though duplication is impossible. So it's to do with range skew, gaps within the values themselves. Questions or comments on that before I move on? Okay. All right. Feel free to keep putting your questions in the QA window as we go along. I'm keeping half an eye on it, so don't worry if you type away. Just keep going and I'll get to it when I've got a chance. So we've talked about two different types of histogram, or two different reasons why we might have histograms, and various types of histograms available. And one other thing to note here is, because these values are unique, we're searching on creating a histogram on the primary key. The height balance histogram and the hybrid histogram would in fact give exactly the same type of thing, because we cannot have duplicate values for the last here. So the last value here is 11. There's only one possible row with the value 11. So height balance and hybrid are in fact the same when you've got it on your primary key values, but we still call it a hybrid for queries as they exist now. Okay, so let's move on and look at another problem. So we saw, again, we had this query where we had color and shape, and this brought the estimate even further down than when we had just on color alone. And the reason for that is, as I showed in that lovely little formula to you a few slides ago, each extra column we add to this, the optimizer assumes there's no relationship between these and goes, well, a third of the values are red, a third of the values are cylinders, so multiply a third by a third, and we expect to get about 1/9 of the rows. So each extra thing we add to this, the optimizer is going to estimate fewer and fewer rows. And if you've got a lot of these conditions you're adding, you've got like 4 or 5 columns you've got conditions against, you can end up with very, very low row estimates, much lower than you would expect in reality. So what can we do about this, and how can we address this? So the thing here is, all the red rows are cylinders. all the cylinders are red. So we have a correlation between them. There is a one-to-one mapping between those values. So we need to address this. So if we look at a small part of the table here, not immediately apparent when looking just at this, but all the red rows are cubes, all the cubes are red, all the blues are cuboids, and vice versa, and all the greens are stars. What we can do is, gather stats on those as a group. Consider that as a pair and say, what are the unique combinations of values for color and shape? And do that, it becomes much easier to see that there is in fact only 3 unique combinations here. We've got red cubes, blue cuboids, and green star things. Only 3 different combinations, not the 9 that you might think from having 3 colors and 3 shapes. If we have a Cartesian product of those, there's no correlation. You can end up with 9 different combinations here of color and shape. We have in fact just got 3. So this is another problem which can affect things, where we've got correlations between values, and the optimizer again doesn't know there's this relationship, so it can drastically underestimate how many rows it's actually going to get. Alright, so Nisarg, we usually gather stats and extended stats nightly after a data load. Does dynamic sampling have tendency to report different optimizer statistics and force to use a different plan which may or may not be optimal? Okay, so that's good question, Nisarg, about dynamic sampling. Let me I'll come back to that in a minute. All right, so bear that in mind, and I'll come back to it because I'm going to jump back over to a demo now and look at how some of these things actually work in practice. So how frequently histograms? You need to clarify what your question is there. I'm not sure what you mean by how refreshed. Take a minute, take your time, type your question. I'll answer it when you've be clear, and I'll answer your question when you've done that. So let's come back. All right then. So we saw earlier all those queries at the start. We had completely incorrect row estimates. So let's regather stats again, and I'll do that, and we'll find that. That takes a minute. There we go. We have now got, some histograms on the columns. So we've got them on brick ID, we've got that range skew, and color and shape because we've got value skew. Now, this is kind of interesting because if we look at the distribution by color, we can see vast majority, 90% of the rows are red, very few green and blue. So we expect a histogram on that. But what about our weight column? Well, again, we've got a very big skew in the values here. Vast majority have a weight of 1, so 80-90% of the rows, something like that. A whole bunch of other values which are pretty rare, pretty uncommon. So why have we got a histogram on the color but not the weight? Well, what's going on here? What's the situation? Well, by default, the optimizer will only gather stats on columns that are used in your where clause. Exactly how depends. Exactly how and why it decides depends. But basically, I only had those queries on brick ID, color, and shape. I did not have a query searching for particular weights. So there's no query on it. So we don't need that extra information about the distribution of distribution of the values. So we don't bother creating the histogram. Save ourselves the effort. Don't do work you don't need to. Don't store information you don't need to. Nobody's querying on weight. Where weight equals whatever, or is greater than or equal to whatever. So don't bother creating the histogram. So this is something to be aware of. If any of you are paying attention to this and suddenly go, why have we suddenly got a whole bunch of histograms up here? It's probably because somebody wrote a query with where column equals whatever, and pulls that information in. So we don't have a histogram on weight because I didn't write a query against it. We do have a column histogram on color and shape because they were in those queries. Okay, so now we've got that histogram. We've got it on our color. we're going to see nice, perfect row estimates now, aren't we? So let's run the query, and oh, hang on. That's not looking great. Row estimate's still way out here, right? We're still estimating just 3,500 instead of the 9,000 we expected. Do it for a couple of the other queries. Yeah, and 500 versus 1,000, and 9,500 versus just one. What's going on here, right? Why are these row estimates so wrong? So going back to anonymous attendee, your question, is there a way to get what the estimated and actual rows returned by a query are? This is it. So it's the auto trace option here. So you can see I'm using this button here, auto trace F6 by default, and SQL Developer. You get this little execution plan. Cardinality is the estimate, how many rows the optimizer thought it would get. Last output rows is the actual, how many rows it actually got. So this is what you want to look at. You want the execution plan, run the query, get that information. So this is one way to do it. I'll show you another way in a minute. Right, so what gives? Why have I not got these right bang up to date stats? What's going on here? Oh, what's the problem? Yeah, what's the problem here? Well, think about it. After you gather stats, the optimizer does not immediately then go and come up with new plans for every query against that table. Let's think about a little extreme example. Let's say you've got one table and there is 1,000 queries on that table which are executed pretty much continually. If we gather stats and immediately afterwards then have to come up with new plans for all 1,000 of those queries, that's going to slow your database down quite a bit, potentially a lot. The optimizer figuring out the best plan is a relatively expensive process. So this could bring your system to its knees. Your really busy system that's close to its CPU limits. If after gathering stats immediately the optimizer then went, well, let's look and see if there's a better plan for these queries, your system could be crippled and fall over. So the optimizer takes a rolling invalidation process. What it does is essentially marks these and says, I'll come back to this later, and then figure out, see if there is a better plan available for it. So it hasn't changed anything here. So just because you've gathered stats, don't expect that immediately you will see changes to your queries. It might take a while, because otherwise, like I say, you could end up in this horrific state where everything's trying to find new plans, and the system falls over. So it kind of spreads that out a bit. So we can force it in this example by creating some new queries. So I'll just, add an alias here, because we do an exact text match. Any change to the text here, upper lowercase, add some white space, stick an alias in. Logically, it's the same query, but the optimizer doesn't know that. It just looks at the text of the query and says, is that the same? Get the new plan and see, now we've got the exact estimates now. We're estimating 9,000 rows that are red and getting 9,000 rows that are red. If we look at our range queries, estimating 1,000, getting 1,000. 9,000 to 1,000, estimating 38. Okay, it's not going to estimate, not quite down to 1, but it's pretty close, right? It's much closer than we were before, 500 odd that we had a minute ago. So now we've got our histograms in place, we've got much better row estimates. So we've got some other questions come in. Let me just have a quick look. Okay, so how frequently histograms refresh? So histograms refresh whenever you gather stats. And by default, in all modern versions of Oracle Database, there is a background job which will do this for you. And that, by default, happens when 10% of the rows have changed compared to the last stats gather. So if you've inserted, if you had 1,000 rows and you've inserted 100, or you've inserted 50 and updated 50, or you've deleted 100 or whatever, once more than 10% of the rows are changed, it'll mark that for regathering and put that in the next run of the stats gathering job. So whenever you gather stats, those histograms will refresh. Obviously, if you call it manually, stats can regather as well. How often that happens entirely depends on the rate of change of your data, right? Some tables, it might happen every day. Some tables, it might happen once a decade, right? So it's entirely down to how much the rows have changed. So I hope that answers your question. Okay, so Niels. So if you've created and loaded a table but haven't queried it yet, does it make sense to gather the statistics as the database doesn't know which columns I want to use for filter? So I guess if you're asking if you've created a table and do you want the stats because we don't have the histogram, so there is still some value in having the stats there, because we'll get things like the total number of rows in the table, the high and low values, and so on. So if you create a table, populated it, and have no stats, then your queries are kind of running blind. There's dynamic sampling, which will kind of fill in the gap a little bit there. So there's still value in having some stats, because it's, with no stats, it's like, what are these numbers here? That said, if you can create a table, populate it, and as part of your release script, for example, you create a new table, stuck a whole bunch of data in there, and just had a very simple query which has the common columns in your where clause, might be worth doing that before gathering stats as part of the release process. If that's kind of what you're asking, Niels, to get those histograms in place straight off the block. I don't see having some stats is better than no stats, if that's kind of what your question is. If you're saying, do you want to run a few queries before gathering stats at all? Well, if you can have some throwaway queries, like in a release process, where it doesn't matter if they run for a long time, or doesn't really matter which plan they get, can be worth doing that too. So I'm not sure if that answers your question, Niels. If it does or doesn't, let me know and see what we can say there. Okay, all right, good, thanks, Niels. So Kevin, what's the main difference between DBMS Profiler and DBMS HProf package? Which one should I normally use? So the DBMS HProf is the hierarchical profiler, which was added in 11 something, I think, and the profiler is the old version of the profiler. Basically, you want to use the HProf hierarchical profiler. It gives much better breakdown. You can see what called what and so on. So use HProf, basically. Short answer there. Alrighty then. So no other questions at the minute. Let's go back over here. All right. So we saw where we had skew in the value. So let's look at our correlation. So before doing this, we saw this correlation between red cylinders. And so all the red cylinders have the value. So let's see what happens when we run our query here. And we can see we're getting much better estimate, but it's not bang on. We're estimating in much closer ballpark. So 7,700 odd rows versus 9,000. And if we search for an impossible combination, red stars, there are no red stars in this table. Again, we get a very low cardinality, 428 versus 0. So in this case, this is probably good enough, generally speaking. But fact is, we could do a little bit better, right? It knows that red's common and cylinder's common, so it's combined those common things, but we still ended up fewer rows than we really actually got. So generally, this is probably good enough, but we could get better row estimates. And to do that, we need to create extended statistics or column groups. And unlike histograms, datamase does not automatically do this by default. You can enable it to do that, but by default it is off. So what I'm going to do is gather stats like this for columns, and we've got the pair here. So we'll gather those stats, and we can see we've got this lovely weird little column in the table now, sys whatever it's called. And you can see that's gathering stats on the combination of color and shape. So looking at those as a pair and getting those unique values. So it's created those stats, but we don't actually have the histogram yet. So if we query it again, we'll get reasonable estimates, but not perfect. We'll get red stars as well. See, 428. Let's just save that one a second. So now let's actually, now we've got some column usage for that, we'll gather it again and we'll get our histogram. So now we find we have our frequency histogram. There's only actually 3 possible combinations in this table. So we search for our red cylinders. Now at last we got our perfect row estimate, and we search for red stars. Okay, it's not dropped down to 1 or close to 0, but we were getting 428 before, dropped down to 250, so we're getting further and further down. So we are generally gradually improving our row estimates here. So this is very useful when you've got relationships between columns. And again, it's something that's fairly common. You know, most customers will get most of their goods delivered to just a couple of locations. So your work address and your home address, which for basically all of us is the same address at the moment, right? And for me, it's been the same address for ages. But you know, there's going to be a lot of correlation between columns, and in some cases, this can end up with wildly incorrect stats. You can over or underestimate things drastically, and if you're leading to that, you do need to gather this manually. The optimizer will not pick this up by default. So we've looked at that and we've got column correlation. So let's look at an interesting example here. So I'm looking for rows where the lower color equals red. So that's going to be the 9,000 rows. So before I do that, let's have a little test here. Who thinks this is going to end up with a good row estimate? So when I say good, I mean anything in like the 7,000 to 10,000 row range. So we know there's 9,000 rows that have this value. Who thinks we're going to get anything close to that estimate? Or who thinks the optimizer is going to get anything close to that estimate? I'll give you a second or two. Just type yes or no in chat. Let me know what you think. No? Gary's going for no. No. A few takers for no. Do I have a functional index? So there's no indexes at all on this table. So quite a few takers for no. No. No, I'm going for yes. No. Okay, so let's see what we get here. Everyone's going for no. Oh, yeah, lack of faith, people. Oh, okay. Let's see what actually happens. Oh, you're all right. Okay, let's look at that estimate there. 105. That is cataclysmically bad, right? You know, we are nearly 2 orders of magnitude out on our row estimate here. So why does this happen? Well, the problem is the optimizer just doesn't know the result of this function without actually executing it. So it needs to run that. And when you're parsing and optimizing the query, you can't run a query to figure out what you're doing. It's kind of a chicken and egg problem. So we end up, it does a lot of fudge factor estimating, and we end up with these highly inaccurate row estimates. So let's just run this again, and we'll find that, that's interesting. It's now got exactly the right row estimate, 9,000. Estimated 9,000, A rows 1,000. So back to Anonymous, who was saying at the start, if you use DBMS X plan to get your execution plan, E rows estimate, A rows actual. So it's bang on. So how did it fix this? How did it correct? Well, we look a bit further down, and we look at this note, statistics feedback used for this statement. So this is something the optimizer runs a query, looks at how many rows it processed, and can use that to influence future executions of that query. So in this case, it's self-corrected. So we're all good and we're all fixed, right? Well, the problem is it is specific to this query. If we change it ever so slightly, I've removed some of the white space. I had a gap there, and I go back to lower like this. Well, that information was specific to that query, so we've lost that cardinality, it's gone. So we're back to that horrendous estimate. So if you've got this same where clause in different queries, or you've got the same query written multiple times in your application, or someone just changes the formatting on your query while making some changes to it, whatever, you've lost that information. That's not very good. It'd be nice to kind of preserve this. So what about creating an index? Kevin was saying, do I have a functional index created? So let's create an index and see what that does. Well, we'll do that, do that. Still doesn't actually help here. And again, we've got the index, but it hasn't actually helped, in this case, at least not straight away, get the correct cardinality. So the index alone is not necessarily enough to give us the correct row estimates in these cases. So what we can also do, we can use these extended stats to gather information on columns as a pair or as a group. You can also use it to gather information on expressions, so lower, upper, adding, dividing, whatever functions you want to apply. So we can do that and get that information, and now you'll find we've got bang on row estimates, so 9,000. So extended stats you need to gather manually, useful for correlated columns, but also if you have to apply expressions. It'd be better if you didn't have to, you just have the column on its own without a function. It's not always possible to do that. So if you are forced to, you may find that you really, really want to use these, create these extended stats on the expression, because it can really drastically improve the row estimates. Okay, and we can see, we're back to the correct estimate now, and we've got a frequency histogram on it. Notice this column name, sys column name, is slightly different because we get that from the function-based index. Function-based index is actually a virtual column with an index on it. Interesting insight into how this all works. Okay. All right. So, Giri, can we gather extended stats for MVL decode functions too? Yeah, you can gather it on any expression as long as it's on one table. Okay. If you've got, if you join two tables and use columns from two tables in your case or decode, you can't gather stats on that because it crosses two tables. As long as all the columns used in the function are in the same table, you can gather these extended stats, Giri. Okay. So yes, you can. Okay, let's see what other questions, comments we've got. So let's move on a little bit. So at this point, I've got an interesting. This is a question that's come in quite a few times on regular offline Ask Tom. And that's, you've got a query a bit like this. So we've got a subquery. So this returns just one row and it returns the value red. We know that there are 9,000 rows in this table with the value red, so this is going to return 9,000. Who bets that this is going to give a good row estimate? Actually, well, we're running short on time. I'll just run this and see what happens. So we run this. What estimate does it give? Yeah, cardinality 3,500. Well, yeah, it's just hedged its bets again. It's taken the average. So why has it done that? We've got histograms on this column. Why hasn't it used that information? Well, the problem is the optimizer doesn't know which value this subquery is going to return. And in fact, in general, we don't know it. I can run this query now and say, oh, it returns red. Someone else might be running another session or might have got a job going which updates it to green or blue. So between me running this, that commits, and me actually executing the full query, that value here could change. So we really don't know. And this is kind of a general problem for the optimizer, where you've got this unknown value. We'd have to run this subquery, which could be really slow and expensive. We don't know how much work that is in advance either. So we're kind of stuck. We're trying to figure out the estimate. And if we turn it into a join, that doesn't really help either, because we still get these hedging its bets halfway between the two values, row estimates. So even though we've got histograms there, we haven't actually helped things. And if we look, and we've got another one. So this time we're going to search for the blue. Should be blue? Yeah, no, green, sorry. So our really uncommon values get just 500. Cardinality 7 times over. So what can we do about this? Well, to help address this, you could create a SQL profile, which helps tweak the row estimates. You do need the diagnostics and tuning license packs for that. Dynamic sampling could help with this. Might help with this in some cases, so I'll crank it up to 11. We run this, and actually in this case it doesn't. So Nisarg, your question about dynamic sampling. what this does is it gathers does like a mini stats gather before running your query, so it can get some extra information. So this extends the data that's already in the stats stored in the tables. So it doesn't force the optimizer to choose a different plan. It can encourage it to find a better plan. It doesn't always, but there is some extra overhead to doing this. This does mean it spends a bit more time figuring out what the optimal execution plan is. So I wouldn't slap this in automatically by default to everything, but it can help for slower running queries, ones where you've got weird data distributions, which histograms and column correlation haven't solved for you. So, Nisarg, dynamic sampling doesn't force a new plan, but it can help the optimizer find a better plan. I hope that answers your question. There you go. Okay. So, Kevin, the solution should be rewrite the query to join the two tables. Well, as we saw, Kevin, if we join the tables, then actually that hasn't solved the problem. We've still got massively incorrect row estimates here. And it's the same problem because it doesn't actually know what the values are until it's run the query. And it's a chicken and egg problem, basically. So, like I say, SQL profiles can help fix this. Dynamic sampling might help it. It hasn't in this case, unfortunately. This is one case where I would suggest or consider splitting the query into two. So we've got the subquery, the query that returns one row, and the second query. So we run that, and I've done that for green. I have to pull it out like this using DBMS XPlan. Find that query. We see the estimate is now bang on. So I wouldn't automatically jump and do this by default, but if you've got queries, either joins like this or subqueries like that, and the row estimates are leading to horrendous plans, consider splitting it into two separate queries. Like I say, only do this if you find you've got a problem and splitting it solves the problem. Don't start splitting them otherwise by default, but this might be something you want to consider doing in some cases. Okay, we're getting up to the hour. There's a couple of last things I wanted to show you, so I will show those quickly, and I'll see some other questions, and I'll address those once I've done that. So the other things said. So one other thing I want to say, disabling histograms. In some cases, you might want to disable the histograms, and you can do that by setting the size to 1. So we can see we've got a histogram on the primary key. Let's just say we don't want that for some reason. So we gather stats, size 1, and now it is gone. So no histogram. Now the problem is I've used this method opt parameter. If someone comes along, gathers stats without supplying that, the histogram is going to get slapped straight back on again. It could be quite frustrating. You spent ages investigating a query, figuring out performance issues, and decided this is the solution. Remove the histogram to get better performance. Next person who gathers stats wipes out your changes. It's like, things go slow again. If you were to, how do we solve this? So if you are doing non-standard things, non-default things for tables, set the table preferences. Rather than using method opt or other various columns that exist in gather stats, find the parameter in the table prefs, so we can see we set size 1 here, set it in the preferences, and then however stats are gathered, as long as people haven't overridden them, they will keep those values. So this is a good just general table, whatever you're doing. If you want to change the default stats gathering processes, set the table preferences rather than trying to kludge it into the gather stats routines. This means that everyone who gathers stats normally will pick up your settings and just makes things a lot more easier to manage. Okay, so how do you move histograms on the this sys column, the generated column? You do size 1 on the expression. Should be size 1 on the expression, hopefully. Let's just check that quickly. Yeah, there we're back to 1. See, the expression here is lower default, so find what the expression is and set the size to 1 here. So size 1 means 1 bucket, effectively no histograms. So Ashish, figure out what the expression is and set the size to 1 on that. All right, so let me just jump back to the slides, recap quickly. I see there's some more questions, so If you're happy to hang around, I'll answer those. Otherwise, feel free to move on. So just to recap, the basic stats, so high value, low value, number of rows, have a lot of limitations. Histograms and extended stats help fill those gaps. Database will automatically create histograms based on column usage. So in general, you don't need to worry about histograms. You kind of handle, disable them by exception. If you find there's a histogram in a column and it's leading to row estimates you don't want, disable it for that column. Otherwise, you don't generally need to worry about them. Extended column, extended statistics, so column groups and expressions, however, by default, you do need to capture them yourself. Again, you can enable this. There's a flag, which I forget off the top of my head. You can enable the optimizer to do that, but if you've got a table or a query and you want to capture those stats for it, you need to do that manually at the moment. Whatever you're doing, if you start tweaking with non-default stuff, use the set table preferences procedure to do that, and then just gather stats normally, just with the table now. This ensures that anyone who comes along and isn't aware of your changes is not going to wipe them out by you automatically. So use the table preferences and just gather stats with just the table name and no other parameters once you've decided what things should be. If you want to know a bit more about this, there's got the white paper on optimizer statistics. If you want a bit more of information on background on performance, I've got my free class on the DevGym, Database for Developers Performance, so check those out. So that's what I was going to cover. I see a couple other questions. Let me just flip back through, see if there's anything else, but and then we can move on. All right then. So let me see. Okay. Let's see. Barry, sorry if I missed it. How does it determine usage in order to decide on which column get histograms during stats collection? Something like scan $SQL, or something more sophisticated like keep some sort of cache list, then it knows what to do on the next round. So basically, whenever you execute a query, it captures that information. And if I go back, where was it? There we go. If you look at this DBMS stats report column usage thing, that will tell you, you'll see on that what it's captured. So it just, as part of running your query, it will capture that information. And yeah, it's kind of an internal thing where it measures that and keeps track of that. But you can see what it is with DBMS stats report column usage. So I hope that answers your question, Barry. But basically, anytime you use it in your where calls, it's going to get captured, even if it's just once, right? Kevin, can we use hints in production code? Well, you can always use hints in production code. However, we strongly recommend that you don't, okay? It's, the problem with using hints is you've then forced the optimizer's hand into a specific position. Now, this can be useful tactically if you've got a performance issue which there's no other way to solve. Put the hint in to give yourself time to find a better solution. But generally, as much as possible, avoid putting hints in your production code, because you essentially tie the optimizer's hand behind its back and say, you've got to use this path, assuming it's possible to do it, which prevents future optimizations. So avoid as much as possible. So I'm not a DBA and find it hard to conduct performance tuning due to privilege issue. I wish Oracle can improve DBA technology to below the line for developer and DBA. Right. So it's a good point. Something we are addressing, Kevin. One thing is in 19C, we've now got, we call it SQL Monitor Report for developers, but SQL Monitoring Report captures the real-time stats of your queries as they execute. That is now available to all users of the database without having to get special privileges, okay? So that's just out-the-box functionality, and we are looking at what else we can do. But generally, the thing is, if your DBAs are refusing to give you this access, then it's their problem to solve it, right? If they don't want to solve it or tell you it's your problem to solve, they have to give you the tools to be able to do that. And yes, I know this is kind of culture and politics and various other issues, but I strongly believe developers should get access to as much of this information as possible, because a lot of the time you need it to figure out a better way to execute your query. So Aravinda, can we find a video recording? Yes, so this session is recorded. It will be available on the Ask Tom office hours session. So if you come back to that page later, if you've subscribed, you'll get an email when we made it available. So that should be sometime later this week that it becomes available, Aravinda. So there will be a recording available. Ashish, will these sys columns cause issues on exchange partitions? Short answer is yes. These hidden columns can cause issues because the table definitions have to match exactly. There is a create table for exchange command that we've added, so which avoids that problem. So if you look for create table for exchange, that helps avoid this problem where you've got a mismatch between these hidden columns causing you issues. So Ashish again, I've seen that whenever we have unused columns in the table, exchange partition fails. Yeah. So yes, look for create table for exchange syntax, and that will solve this problem for you. So you can, the non-partition table you can create like that, so you can do partition exchange. So check that out, Ashish. That should help solve the problem there. Alrighty then, I think that's most of the things that I was gonna cover. So all that's left to say is really hope you enjoyed this. More importantly, I hope you learned something. Please stay safe, and I hope to see you all again next time. Goodbye.